Hi everyone, I'm Siraj Younes, and PhD student at ISM University Faculty of Science and Technique Rashidiyah. And today I have the honor to give a presentation of our work about the improving the performance of eye-shaped patch antenna using metamaterials for biomedical applications. So the plan of our presentation, we will start with a small introduction, then a motivation and problem statement, then the patch antenna and metamaterial designs, and we move to the parametric study and we discuss some results, and finally we conclude with a small conclusion. Let's start with a small definition of patch antenna. A patch antenna is a type of antenna that is widely used for wireless communications systems. As you can see in the picture, is a piece of metal, usually made of copper, and attached it to a ground plane and feed with a transmission line. Also, the patch is usually positioned over a substrate such as the FR4, which provides mechanical support and helps to control the impedance of the antenna. For the motivation and problem statement, our research addresses a critical challenge in patch antenna for biomedical applications. As you know, the conventional antenna have some limits and some limitations, such as the low bandwidth and also the strong back radiation. And in order to address this issue, our study investigates the integration of metamaterials to enhance the antenna performance by optimizing the impedance matching, increasing the gain, and also improving the directivity of the antenna. Here we have the design of our proposed antenna. As you can see in the architecture, the proposed antenna is a U-shaped patch with a modified ground plan designed to work at 2.4 GHz and 6.23 GHz, which are two special frequencies used in biomedical for various applications. Also, the resonant element is implemented on IFR4 substrate with a thickness of 1.6 millimeters. Also, the size of the ground is reduced. That means the antenna introduced with a partial ground plane instead of full ground plane. Here we have the metamaterial design. As you can see, the metamaterial is an array of 4 elements designed on IFR4 substrate with a dielectric of 4.3 and a loss tangent of 0.02 and also a thickness of 2 millimeters. Each unit cell of the metamaterial comprises 2 square resonant elements. The 2 elements are separated by a distance to minimize the interference and also to enhance the electromagnetic properties of the metamaterial. And here we have the position of the antenna and metamaterial. As you can see, the metamaterial is positioned under the antenna at a precise spacing of 2 millimeters. This integration helps to the antenna to minimize the back radiation. That means the metamaterial acts like a reflector for the antenna. And here we have the unit cell characteristics at the frequency of 2.4 gigahertz. The real part of permeability is negative from 2.4 gigahertz to 3 gigahertz as presented in the curves, with a sharp peak transition to positive values indicating a strong magnetic resonance. Also, the real part of permittivity is positive with a sharp dip into negative values around 2.4 gigahertz to 2.6 gigahertz, which mean a strong electric resonance. For the frequency of 6.23 gigahertz, the real part of permeability is negative between 5.7 gigahertz and 7 gigahertz, with a peak at 6.4 gigahertz Hertz, and also the real part of permittivity is negative, turning positive around 6.6 gigahertz with a peak around 6.8 gigahertz. Let's move now to the parametric study. A parametric study was conducted to evaluate the impact of certain key parameters into the antenna performance, focusing on the reflection coefficient. This study involved systematically varying two critical design parameters. The first one is the metamaterial substrate height, and the second one, the spacing between the metamaterials and the antenna. The first parametric study is the effect of the air gap G between the antenna and the metamaterial. The impact of varying the distance between the antenna and the metamaterial was investigated by adjusting the gap parameter from 1 to 3 millimeters. As you can see in the curves, the most favorable outcome was observed with G equals 2 millimeters, where the reflection coefficient reached very good values of minus 36.63 dB at 2.4 and minus 36.54 dB at 6.23 gigahertz, indicating optimal performance with minimal reflection and improved overall antenna efficiency. And here we have the second parametric study is the effect of the metamaterial substrate height H2. A parametric study was conducted varying the parameter H2 from 1.4 to 1.6 millimeters. As you can see in the curve, the analysis demonstrates that the optimal performance characterized by a minimal reflection and the best impedance matching was attained with a substrate height of 1.6 millimeters with a reflection coefficient value of minus 36.63 dB at 2.4 gigahertz and minus 36.54 dB at 6.23 gigahertz. And let's move to the section of result and discussion. In this section, we analyzed the obtained results in detail and provided a comprehensive comparison between the antenna performance with and without integration of metamaterial. The first result is the reflection coefficient and the VSWR. As you can see in the curves, without metamaterial, the reflection coefficient was minus 10.71 dB at 2.4 gigahertz and minus 13.88 dB at 6.23 gigahertz, indicating less efficient impedance matching and also higher power reflection. In other hands, with metamaterial integration, the return loss improved to minus 36.63 dB at 2.4 gigahertz and to minus 36.54 dB at 6.23 gigahertz. And also the VSWR value was improved from 1.66 to 1.03 at 2.4 gigahertz and also from 1.75 to 1.04 at 6.23 gigahertz. And for the second result is the gain also value experienced an enhancement increasing from 0.5 to 1.26 dB at 2.4 gigahertz and also from 1.77 dB to 3.48 dB at 6.23 gigahertz. This improvement is due to the metamaterial ability to alter the antenna effective electromagnetic properties. And here we have the last result is the current distribution of the antenna. As you can see with metamaterial, the current becomes more concentrated and uniform. This focused distribution reduces the energy losses, enhances the field confinement, and improves the various antenna performance, including the gain and directivity and also the impedance matching. And in conclusion, to conclude, in summary, this study demonstrates that the integration of metamaterials improves the performance of patch antennas, especially in terms of gain, bandwidth, and impedance matching. The antenna's performance enhancements make it well suited for various applications, including the 6G communication systems and also the biomedical applications. And for more experience with our proposed antenna, we will try in the future to calculate the SER to guarantee the safety of our proposed antenna in case of biomedical applications. And thank you for your attention.